You're on the 80th floor of a skyscraper. The wind outside is howling at 100 miles per hour. And the building you're standing in is moving. Not breaking. Not cracking. Moving. On purpose. And if it ever stopped moving, you'd be in serious danger. This isn't a construction flaw. It's not a sign the building is failing. It's one of the most counterintuitive engineering decisions ever made, and it's built into every skyscraper over 300 meters tall on the planet. By the end of this video, you'll understand why the most dangerous skyscraper isn't the one that sways the most. It's the one that refuses to move at all. Here's the problem engineers faced. When wind hits a skyscraper, it doesn't just push. It creates pressure zones, high pressure on one side, low pressure on the other. The building gets pulled and pushed simultaneously. At ground level, that force is manageable. But physics doesn't work in your favor as you go higher. Wind speed increases with altitude. At 400 meters, the wind load on a building can exceed 10,000 tons of lateral force. That's the weight of 70 fully loaded Boeing 747s, pushing sideways. Now imagine you're an engineer. You have two options. Option A. Build the structure so rigid that it physically cannot move. Pure steel and concrete, immovable. Option B. Let it move. Every instinct says option A. Stronger is safer. Rigid is reliable. But option A has a fatal flaw. A completely rigid structure doesn't absorb force. It fights it. And in a fight between a 400-meter concrete column and sustained hurricane force wind, the concrete loses. Catastrophically. The question isn't whether the building will move. The question is, who controls how it moves? The answer is a device most people have never heard of. It's called a tuned mass damper. Inside Taipei 101, once the tallest building in the world, there is a steel sphere. It weighs 660 tons. It hangs from cables on the 92nd floor. And it swings. When wind pushes the building right, the sphere swings left. The opposing momentum cancels out the sway. The building moves, but the movement is controlled, dampened, invisible to anyone inside. This isn't primitive engineering. The sphere is tuned to the exact resonant frequency of the building. It's a precisely calibrated counterweight, engineered to oscillate in perfect opposition. And Taipei 101 made it into a tourist attraction. The damper is visible from observation decks. Millions of people have stood and watched a 660-ton ball quietly save the building they're standing in. The building sways. The damper sways back. You feel nothing. But tuned mass dampers are just one layer of the system. The second layer starts at the foundation. In Japan, a country that experiences more earthquakes than almost anywhere on Earth, engineers developed base isolation. The building doesn't sit directly on the ground. It sits on a series of rubber and steel pads, isolators, that absorb seismic energy before it reaches the structure. When the ground shakes, the isolators compress and flex. The building above them barely moves. The third layer is the structural frame itself. Modern skyscrapers use geogrid systems, diagonal steel grids on the exterior that distribute load across the entire skin of the building. No single point bears the full force. Every panel, every joint, every weld shares the load. 3 systems. All working simultaneously. All designed around the same principle. Controlled movement beats rigid resistance. Here's where it gets genuinely strange. Engineers don't just want the building to survive wind and earthquakes. They need to make sure occupants can't feel the building moving. Because the human body is remarkably sensitive to lateral acceleration. At just 0.02 g of sideways movement, barely perceptible to instruments, people begin to feel nauseous, disoriented, anxious. So the engineering challenge isn't just structural survival. It's human perception. The Burj Khalifa sways up to 1.5 meters at its tip in high winds. That's deliberate. That's safe. But if occupants on the 160th floor felt that movement, the building would be uninhabitable. The damper system is tuned not just to protect the structure, but to keep the sway below the threshold of human sensation. The building moves. You don't know it's moving. That's the engineering goal. But what happens when the system is pushed beyond its design limits? In 2011, the Tohoku earthquake struck Japan. Magnitude 9.0, one of the most powerful ever recorded. In Tokyo, 370 kilometers away, skyscrapers swayed visibly for over 3 minutes. The buildings performed exactly as designed. Base isolators absorbed the ground motion. Dampers controlled the upper sway. Not a single modern high-rise collapsed. But there was something nobody had fully anticipated. The long, slow oscillation of the earthquake, its low-frequency waves, matched the natural resonant frequency of several buildings. Instead of damping the sway, the buildings briefly amplified it. Elevators jammed. Water sloshed out of rooftop tanks. People on upper floors felt sick. The structure survived. But the experience revealed something critical. You can engineer for known forces, but resonance finds the gaps. So here's the full picture. A skyscraper is not a rigid column. It's a tuned instrument, engineered to move in specific ways, at specific frequencies, within specific tolerances. The sway isn't failure. It's the system working. The 660-ton pendulum isn't a patch, it's the design. The rubber isolators aren't a workaround, they're the foundation. The diagrid frame isn't decoration, it's load distribution in steel. Every modern skyscraper over 300 meters tall is a machine for surviving forces that would destroy any rigid structure within minutes. The safest building isn't the one that stands completely still. It's the one that knows exactly how to move. Now here's what's worth thinking about. This same principle, designing flexibility into a structure to make it stronger, appears in suspension bridges, earthquake-proof hospitals, offshore oil platforms, and even the human spine. Nature figured this out long before engineers did. A tree survives a storm not because it's rigid, but because it bends. Which raises the question: what other structures around you are secretly moving to keep you safe? That's a video for another day. If you want it, you know what to do.